Hello students, welcome back. Now we are going to design the pattern detector again, but this time using the mealy machine. So in this video, we are going to talk about the pattern detector design using mealy machine. What is the difference in this with respect to the Moore's machine based design, and we are going to implement it using Verilog. So let us get started. So pattern detector, when we design with mealy machine, we don't need the 5 state as we had in the Moore's machine based pattern detector. We will use less number of state when we are having mealy machine. The main difference is coming because we have additional input which will control the state transition. In Moore's machine, remember, we had a restriction that we can decide the next state and the output in one case statement. Whereas in mealy machine, if we want, we can have one case statement only for state transition and one case statement only for the output allocation. So this will optimize our number of states. So let us construct the state diagram for the same pattern that we had detected earlier. So we are having our states S initial, S1, S10, S101. We are not having S1011. Why? Let us see whether these 4 states should be sufficient or not. So first of all, when we are at S initial and the input is 1, we will traverse to S1, and if the input is 0, we are going to come back to same state, that is S initial. From S1, if my input is 1, we are going to traverse back to S1, and if the input is 0, then we go to S10. From 10, if the input is 1, then we go to 101. But if the input is 0, that means we are going to S initial. Now the important state. We are at 101. If our input is 1, that means we have detected the pattern. And where should we go? We should go to S1. Okay, from 101 we will go to S1 if the input is 1, and only in this case my output will be 1. In all the other cases my output is 0. In mealy machine, remember, we used to write output on the state transition. Now from 101, if the input is 0, then I can traverse to 10. So input is 0, output is 0. So this is how we construct a mealy machine based finite state machine which can detect the pattern 1011. Less number of states are used, but coding will be slightly lengthier. Now we can take one more similar example where we are detecting 0, 1, 1, 1. So my first state is S initial. If I have input 0, we go here. If I have input 1, we will roll back to the same state. From 0, if I get input as 1, then I can go to S01. But from 0, if my input is 0, then we can come back here. From 01, if input is 1, we will go to S011. Okay, so this is input 1, output 0. Now from 01, if input is 0, then where should we go? Then we will go to S0. Right, now the important state 0, 1, 1. If the input is 1, that means we have detected the pattern, but I cannot use this pattern again, so I will go back to S initial if input is 1, output will be 1 and we will go to S initial. But if input is 0, then we will go back to S0, but output will be 0. So this way you can design your own pattern detectors using mealy machine or Moore's machine. Now we are going to implement the same using Verilog in Vivado. We have the code ready, which is very similar to our earlier code of pattern detector. We have input D in, clock and reset, and output is Z. Then I take wire which is D in, clock and reset. These are my inputs, so these are wires, and output is a register Z. Now since I have only 4 states, I need to define only these 4: S initial, S1, S10, S101. To define 4 states, only 2 bits are enough. So my register size of state and next state is also 2 bit, not 3 bit this time. Now we are defining always at the rate positive edge of the clock. If reset is 1, then we are saying state is equal to S initial if we are resetting. If we are not resetting, then whatever is the value of next state, that will go to our state. Now this is our first state transition case statement. Always at the rate state. If we are in the case S initial, if input is 1, we go to S1, otherwise S initial. We are not defining output here. In S1, if input is 0, we go to S10, otherwise we go to S1. In S10, if input is 1, we go to S101, otherwise we roll back to S initial. And in 101, if input is 1, we go to S1, otherwise we go to S10. We have default state and we end the case. Now we have one more case statement which is only for output declaration. And we say if our state is S initial, output is always 0. In S1 always 0, in S10 always 0, but in S101, if input is 1, output is 1, otherwise output is 0. End case, end module. This is our program. Now for this program I have written the test bench as well. In the test bench we have defined our registers and wires, and I have instantiated the module using these variables. Now we say at every 20 nanosecond flip the clock. That means the time period of my clock is 40 nanosecond. I define the initial conditions. Clock is 1 and reset is 1. After 50 nanosecond I set the value of reset to 0. So now I will start giving the value of D in. So after every 40 nanosecond I am changing the value of D in. I am giving the values 1, 0, 1, 1, 1, any pattern that you want. I have given around 15 such numbers. You can give as many, but please remember, always give at a difference of your clock period, and in my case it is 40 nanosecond, and then I finish the simulations. Now let us have a look at the simulations. So here we can observe that initially D in is not defined, reset is defined, so the output is 0. Now here we are defining D in. This is 1, 0, 1 and 1. As soon as you detect it, output is 1. Another instance, 1, 0, 1, 1. As soon as we detect it at the positive edge, the output is 0. So the whole pattern, we had given 3 such sequences detections, and it is detecting all 3 of them, 1, 0, 1, 1. So students, we hope that you have learned a lot about finite state machines now. We have our module test coming up, and after that we will start discussing the projects. Keep learning. Thank you.